A very good morning to all the dignitaries, guests, delegates, researchers, and students. With great joy and immense exultation, I feel privileged to extend my warm welcome to all presented here. And dear participants, this one-day workshop on smart materials is organized jointly by Amity University, Haryana and National Sun Yat-sen University, Taiwan. And the topic of this one-day workshop is smart materials and is very interesting. As you all know, smart materials are the materials that are manipulated to respond in a controllable way, modifying some of their properties as a result of external stimuli, for example, certain mechanical stress or a temperature. So to know more or to have a deep knowledge about these materials and the properties of these materials, please welcome our distinguished speakers, Professor Cheng from Taiwan, Professor S.K. Sharma, he is not present now, right now, and Dr. Neelam from CSIO. And before going to start our first session, let us have the pleasure of listening to the words of wisdom from Honorable Director of Applied Sciences, Professor A.K. Yadav. So over to you, sir.
Thank you, Dr. Jyotsna. Heartiest greetings and a good morning to all present. What a great day to start this event, a wonderful event, which is a workshop jointly organized by Amity University, Haryana and National Sun Yat-sen University, Taiwan. Uh, it's my great pleasure and honor to extend a warm welcome to our guest speaker from Taiwan, Professor Chuang, and Dr. Neelam from CSIO, Chandigarh. And we have another distinguished expert who will be joining us shortly, Professor S.K. Sharma from JNU. This particular event is just one component of our collaboration, under the ambit of which we are actually working on several fronts. So thanks to our partner, National Sun Yat-sen University, Taiwan, that we've been able to put together several things to take this MOU forward and make this collaboration very fruitful. So this particular event is a brainchild of the discussions that Professor Chuang and Dr. Jyotsna had over the last few weeks. And I'm glad that finally the program has taken shape and it is aimed to benefit the researchers on both sides, the National Sun Yat-sen University side and Amity University side. We at Amity University are greatly excited to see the sessions of this workshop taking shape, and we are very confident that all the participants are going to immensely benefit from these sessions in the workshop. Let me also apprise you that there are several other things that are going on under the MOU. We signed this MOU only last year in February, March. We've not yet completed 2 years, and during this almost like 1.5 years, a lot of things have been hampered by the lockdown, but still online platforms have allowed us to extend the cooperation between the two organizations. And also a lot of things have gone into taking the collaborative efforts to the next level. Already some students from Amity University are pursuing their PhD at National Sun Yat-sen University, Taiwan. And we are also trying that more students get benefited from this collaboration. Also, there has been an effort to submit joint proposals for funding our research projects and the research plans. And then we have had events in the past, and we are having today's workshop as a joint event. So a lot of things are going on, and I must greatly appreciate and compliment the efforts of Professor Chuang and Dr. Jyotsna Sharma to plan these things and take our association to the next level. So once again, it's a great honor for me to extend a warm welcome to Professor Chuang and Dr. Neelam and Professor S.K. Sharma, who have very kindly agreed to spare their valuable time and conduct these sessions in this workshop. So it will be really so nice of you that you have graced this occasion with your auspicious presence this morning in the inaugural session. So I'm highly grateful to both of you. And also, I would like to compliment Dr. Jyotsna, Dr. Preeti Thakur, Dr. Chandrasekhar, and other team members of the organizing team for putting together this program for the workshop. And I also would like to extend a warm welcome to all the participants who are keenly looking forward to the sessions of this workshop. So once again, I extend a warm welcome and heartiest greetings to all present. Thank you. You are on mute, Dr. Jyotsna. You have to unmute.
Am I audible, sir?
Yeah, this is fine now.
Thank you very much, sir, for your inspiring words and influential message. Now we are entering in the first session of today's workshop, which is based on biosensors and wearable medical devices. So I request Professor Preeti Thakur, HOD, Department of Physics, SRS, to introduce our first speaker, Professor Cheng. Over to you, ma'am. Preeti, ma'am.
Okay, good morning all. At the onset, I want to welcome our distinguished speakers, Professor Cheng and Dr. Neelam and Dr. Shatendra, who have so graciously consented to be part of this workshop. So let me give a brief introduction to Professor Cheng. So Professor Cheng received his BS and PhD degree in civil engineering from National Cheng Kung University in 2002. He then held the postdoctoral research scholarship with Center for Micro Nanoscience and Technology in the same university, where he was in charge of the core facilities for MEMS fabrication and nanotechnology. At present, he is a professor with Institute of Medical Science and Technology at National Sun Yat-sen University, and also the director of Micro and Nanosensing Technology Lab. His research interests basically focus on flexible tactile sensor, roll-to-roll imprint technology, and epidemic biosensors. And he has published over 250 papers in different international journals and conferences. He has book chapters to its credit and 41 patents to in biosensor and tactile sensor. And he was also recruited in several technical program committees and has been on editorial board of Journal of Biosensor and Bioelectronics since 2012. So welcome, Professor Cheng, and we are hoping that we will have a very fruitful collaborations with you, and hope this workshop will be of interest to all the students and faculty who are participating. So, ni hao, Professor Cheng, and welcome to this workshop.
Thank
okay, so can you see my screen?
Professor Cheng. Over to you, Professor Cheng.
Yeah, thank you. Thank you, the Professor A.K. Ado and the chairman to introduce me. And I also want to thank Professor Sharma to organize this special workshop. And I'm really glad to see you guys again. And actually, I think maybe a few months ago, we also have this kind of like a recruit student workshop. And today, I think I will introduce our research work in my lab. And I also will introduce our PhD program for science and our institute. So because time is quite limited, so I need to move forward and go to the details. So my name is Chen Xin Zhuang, and I come from National Sun Yat-sen University, Kaohsiung, Taiwan. And I don't know, do you know the Kaohsiung city? Kaohsiung city is the second largest city in Taiwan and is in the most southern part in Taiwan. So our is a sunny city, and for the Sun Yat-sen University, we have beautiful beach and very good weather. So hopefully next time we can have a meeting or workshop in our university. So I think before my talk, I need to mention that precision medicine, okay. Precision medicine in the currently medicine is a one drug fix all model, okay. So you can see the top. So for the cancer patient, usually we have some protocol. So all the patient, they will take the protocol step by step. So, but however, the result, the outcome is somebody are very good, but some people are not so good, and some people is not affected. So recently, we have Taiwan Precision Medicine initiate. Actually, we call it precision medicine. Okay, so in the future, I think precision medicine is very important because after although these patients have the same cancer, but they have individual different. So we can test the DNA sequencing, and we also can test the biomarker by the molecule detection. Then we can divide this patient into different group. Then we can have different treatment. So that will make more efficiency, and the outcome will make everybody is going good side. So this is we call the precision medicine. Actually, precision medicine already raised this issue maybe already over 10 years. So right now, Taiwan try to move forward to we call the precision health. So precision health is actually precision medicine plus precision prevention. So what is the precision prevention? That means we need to better understanding the behavior and the social factor so that we can help doctor to predict and prevent the disease, not just treat it. So you can see usually we will have 3 stages for the health matter. So one is healthy people, another one is sub-health, and now the hospital only focus on the disease. So in Taiwan health department, we try to move forward to another stage that we want to focus on healthy people and the sub-healthy people to make some precision prevention. If we can do the prevention and plus the precision medicine, then we can call this is so-called precision health. Okay, so precision health actually we need to depends on genomics. So genomics we have to do is everyone need to do the DNA sequence and the molecular detection. So then we can know he or she they have this kind of variants, or like when they do the DNA mutate, then we can do the individual different treatment. However, this only for disease. If you want to do the prevention, we need a IoT sensor. So we need everyone monitoring their vital sign, and we also need to know where he lives, what kind of air condition he breathes, and what kind of water quality he drinks, even the food he eats. So then we need to monitoring his lifestyle. So like a sleeping condition, or did he doing the exercise, or how many works he do. So these are we so-called we call the exposure concept. So not only the genomics, we already done this for 10 years, but recently we try to focus on this exposure concept. That means the individual one, they exposed in this environment, we also need to know. If we have this data, then we can do the AI pattern recognition, then we can do the prevention and the prediction. So plus this genomics, IoT sensors, and AI technology, then we can go to the precision health. So for that's the IoT sensor makes the precision health very important fundamental device. So now we call the Internet of Medical Things. So I think everyone maybe know the Internet of Things, but if we apply for the medical use, we will call it, so we call the Internet of the Medical Things, we call the IOMT. So the IOMT will looks like this, okay. So individual, they will wearable or use some cell phone and they can extract their healthy data and upload to the cloud. And this cloud, they do have the artificial intelligence to recognize, to monitoring and prediction. So if they found if you have your heartbeat or your heart rate is not normal, then they will alarm to the hospital, to the family, and to yourself. So I think maybe you know, now in the commercial market, they only provide the for the diabetes people, they just give you alarm to measure your sugar, blood sugar. They just do this one thing, and they can decrease the mortality about 50%. So that means alarm actually is really important. However, if you want to do the wearable device, then we cannot talk about flexible electronics. So you can see, if you want to do the wearable device, you need to do flexible. So flexible electronics will be a very hot topic in the recent years. So many people are trying to do the paper-based sensor or PET-based sensor, this kind of things. And they will also do some microfluidics and microelectronics on the flexible substrate. So they will be low cost, so you can disposable and maybe just you can use for 1 week, and then you can change the new device. And these are all demand on low power and the point of care. So point of care means you don't have to go to the hospital. You can do the diagnostics at home, and we can transmit all the data to the cloud. So these things are the requirement of IOMT. So we think in the future, diagnostic in the post-COVID-19 era is decentralized. Actually, now we still facing the COVID-19, so we cannot say now is the post-COVID-19, okay. So in the past, I think everyone should go to the hospital and do some very intense examination in the laboratory technology. And maybe 3 days or 1 week later, you can get the report. However, we think that in the future, we're gonna have the point of care, the nano sensor like this already on the market. So you just use the drop of the sample, and it's very easy to diagnosis, and there is user-friendly and very easy to tell the result. So once you want to shrink this lab, the huge lab, the bulky machine into small device, I think nanotechnology provide a very high competitive point of care nano sensor device for diagnostics. So right now, for the POC test, I think in the commercial market, you already have the glucose sensor and the pregnancy test. Okay, so these two are very famous. And actually, they also use electrical sensing and colorimetric sensing. Okay, so in our lab, I think the biosensor is the basic structure looks like this. So you need to immobilize the biological receptor on the electrode, and then you can detect the target. So sometimes the target will be protein, DNA, or enzyme. And then you need to have a transducer. This transducer could be optical or electrochemical or mechanical. In our lab, we try to focus on the electrochemical issue because that will be very good for the data processing because it's all electrical signal and very easy to upload to the cloud. Then we can have the big data. So this is what we focus on in our lab. So later I will introduce, in our lab, we doing a lot of nanomaterial-based biosensor and a medical device. So in our talk, I will give you 3 topics. Okay, the first topic is bladder cancer. So bladder cancer, we already done for last 10 years, and we already developed a biosensor, and we already go to the clinical trial. And another topic is chronic kidney disease. And this kidney disease also very serious problem in Taiwan. So I will talk about a little bit later on. And then is a wearable device. So we try to develop some wearable device for the quarantine, and we can monitor in the vital sign. So you can see these are the unmet need. That means some kind of disease or what we need for the medical device. But the left-hand side is what we use the nanomaterial. Okay, so the first part will be biosensor. The last part will be wearable device. So the first part, I think I will introduce the first topic is bladder cancer. So you can see the bladder cancer is the 6th most common cancer in the world. And the problem is this disease will not fatal cancer. Actually, 5-year survival rate is over 17%. That means if you have early detect, then you can survive for a long time. However, the recurrency rate is quite high. So within 5 years, the recurrency rate will go to 75%. And in order to monitoring this patient after the surgery, you need to go to the hospital to do the invasive examination, like a cystoscopic. So that's quite painful for the patient. So, and in Taiwan, we also have this bladder cancer, very serious problem in the southern east coast because they have some underwater pollution issue. For the elder people, they have very high incident rate of the bladder cancer. I think the incident rate is about 10 times of the average in the world. So we try to solve this problem, and we develop this ultra-sensitive immunosensor using a nanoprobe for the point-of-care detection of bladder cancer in human urine. So in this research, we use a very low-cost nanoparticle, is aluminum oxide. So, and we try to modify the surface, and we can binding with the antibody onto the surface. So we using this nanoparticle, and we use this kind of the interdigital electrode on the sensor. So you can see this is our sensor. So we use a very standard semiconductor process, and we can fabricate this sensor in my lab. And we have the gold electrode, and you can see the modified image were here. So there are 3x3 gold electrode, and it's all interdigital electrode. So the first step, we need to immobilize this nanoprobe onto the electrode. So we using the dielectrophoresis process. this direct electrophoresis force is we just apply an AC voltage, then this particle will move and stick onto the electrode. So you can see this is the before we trapping the nanoparticle. So the electrode will be very blank, it's clean. So after we trapping this nanoprobe onto the electrode by using the DP force, so you can see the dark is, these are the nanoprobe onto the electrode. And we also can confirm this by the fluorescence image. So then we can measure the impedance by test urine. Okay, the test the urine. So that means before immunosensing and after immunosensing, we can measure the difference, the impedance. So the differential is different impedance. So you can see the impedance will be here and impedance variation will be here. And we also collaborate with medical center in Tainan City, is Chimay Hospital. And we already test for about 56 patients. And we extract each patient urine and drop the urine onto our sensor. And we can detect the impedance variation. So after we collect this data, so if we set the 20% as the threshold cut of the point, then we can have a very high accuracy. So you can see the accuracy will goes to 86%. So that will be the best, and it's good, better than the commercial test key in the product. Okay, so this is the bladder cancer, what we have done maybe 3 years ago. Okay, and the second topic is chronic kidney disease. Okay, so as you can see, the CKD is a serious problem because you can filter by your kidney your urine, and you will leaking your protein into your urine. So in the globally, actually this is a very serious problem and increasingly by every year. So in Taiwan, we also have very serious problem, but maybe you don't know, Taiwan we call a kidney dialysis island, because we have very high, the highest dialysis people ratio in Taiwan in the world. And our health department also pay a lot for this kind of kidney dialysis. I think maybe every year over 60 billion Taiwan dollar per year. Okay, so that's the biggest problem for us. But right now, because kidney disease, they don't feel anything. There is no nerve, and so no one will feel that. So only way is to test your urine. But the test urine right now only for the colorimetrics test strip. So there is no digital test strip in the market. So then we try to develop a biosensor, and we can detect the urine albumin and the urine creatinine. So with these two factors, these two concentration, then we can have the UACR indicator. So this UACR, that means albumin extract in a milligram per day. So that is very important clinical indicator for the kidney disease. So in the first step, we try to develop the paper-based sensor. So you can see this is the paper-based sensor, and we use screen printing electrode onto the paper-based sensor, and we try to electrode deposition with the gold nanocrystal on the carbon electrode surface. Then we use the DP trapping. So like the previous, the bladder cancer chip, the same we use after modify the nanoparticle, then we can use the DP force to immobilize onto the electrode. So, but at this time we use the polystyrene particles, and we using the electroless electroplating method to plating, like you can see the silver nano dots onto the polystyrene particle. Then after we immobilize on this interdigital electrode, then we can detect the protein, the urine. So we also developed this readout circuit, and then we can have the portable device. So you just insert your chip and drop your urine. One side is for the test side, another side is for the control side. Then we can have this albumin concentration, and this is the impedance variation ratio. So, but unfortunately, the detection limit is only 30 microgram. So the 30 microgram is good enough, but not so good. So we try to develop another sensor. So another sensor, we still use the screen printing carbon electrode, but this time we don't use any particle. We will deposit the conductive polymer polyaniline onto the carbon electrode first. So then we can have the amino group on the surface. Then we try to increase the sensitivity, so we electrode deposition with the gold nanocrystal onto the polyaniline surface microstructure. So you can see this is the polyaniline microstructure. It looks like a tree. Okay, so this tree structure is a porous structure and a 3D structure that will make this sensor more sensitive. Then we directly bonding the antibody onto the polyaniline surface. Then we can test the urine, protein urine. So we still measure the impedance difference. Okay, so as you can see, the sensor is very sensitive. So in the last time, we only can achieve this part, but for this sensor, this nanocrystal nanostructure sensor, we can achieve 3 microgram. So that means we already can detect the stage 1 CKD 2 order lower albumin concentration. So after we get this such good result of the albumin sensing, I think we can move forward to the creatinine sensing. So like I said before, creatinine sensing and albumin sensing, if we can do the ratio, so we can get the UACR. So creatinine sensing, in the past, people are using the enzyme. But the enzyme, they have some issues, because if you use the enzyme, that means you need to preserve your a sensor in the refrigerator, because you need to under 4 degrees C, and that's not a good for the point of care. So we try to think another way. So in our research, we try to use the metal oxide. So we use copper oxide, so Cu2O, this kind of nanoparticle. And we use a stepwise synthesis method. And so you can see the different step, and the size and the morphology were different. And we will just drop this copper oxide and onto the copper electrode biosensor. Then we can do the creatinine sensing. The sensing mechanism is when we apply a certain potential, the Cu2O will oxidize to the CuO. And this CuO, they will react with creatinine. So then our sensor, the CO2O will disappear into the solution. So then we will have if you have the more creatinine, then they will react more CO2O, then we will decrease the current. Okay, so the novelty here is because in the urine we have many interference like uric acid or ascorbic acid. All these are negative charge. So we try to use a zygonic surface functionalized. So we have this negative ion tail with surrounding the nanoparticle. So this negative ion will looks like a shadow proton exchange membrane. Then the negative ion will repair to the solution, but the positive ion, the positive will go inside and react with our CO2O. So the creatinine is the one. Okay, so we increase the specificity by using this Zienter ion modification technique. Here is our result. So you can see the sensitivity. This is the single crystalline nanoparticle, and different step we can have different morphology and different size. After testing, we found the sample C is the best. It's a cubic nanocube. And by using this nanocube, we can test onto the sensor. So you can see before and after, they do have different impedance. So that's we can see they really react with the creatinine. And we also try to sensing the serum, the creatinine in the serum. So the creatinine in the serum, in the human serum is in this range. So we test the full range from 10 micromolar to 200 micromolar. And so you can see here is the CV result. And you can see the signal is quite linear. After we test all kinds of the interference, we also can see the difference, maybe just 5%, but they still linear. Okay, so this is the very good linear behavior for this biosensor. The most good part is you can see this figure. We show the sensor after fabricated, we reserve in the room temperature in our environment for 6 months. But after 6 months, the signal still very good. There is no decrease for this sensor. So that means this is very good for the point of care. You can reserve your sensor at home. So the last part is after we talking about the two biosensor, then we will move forward to the wearable sensor. The wearable sensor, we so-called a patch type vital sign sensor. So maybe as you know, the quarantine is very, when you lock down and or you are COVID patient, usually you need to stay at the isolate room. And this isolate room, we need to monitor your vital sign. So if this isolated room and the nurse, they need to go inside to measure your temperature or your respiratory function. Actually, they have some contact, and this is the high risk. So in our lab, we try to develop the wearable sensor, and it's wireless. So we try to develop the strength sensor for monitoring the breathing monitoring, and the temperature sensor to monitoring your temperature, body temperature. And then we can transmit the data to the cloud, and the doctor can know your condition. So we can have less contact. That's the main issue. So for the first part, the temperature sensing, we try to use a gold code ultra long silver nanowire based flexible composite for the temperature sensing. So in our lab, we can synthesize the silver nanowire by ourselves. But because this is the wearable device, so we need to attach to your skin for a long time. So you know the silver is very sensitive by the oxidation. So we try to develop without any oxidation silver nanowire. So after we synthesize the silver nanowire, we also synthesize the gold surface coated with the silver nanowire. After we can get this AU code silver nanowire, then we mix with the PG. So the PG is in this case, we use low molecular weight PG, because the low molecular weight PG, the TG point is around human temperature. That will make this material has phase change when the temperature change. So we mix with the PG, then we mix with the PU. PU as the matrix because it's a flexible substrate. Then this material will be very conductive. Then we spin coating on the IDT electrode, and the final sensor will look like this. So we put it into the oven, and we can test the electrical signal. So this is what we done for the temperature sensing. So then you can see this is the silver nanowire which synthesis in our lab. So all single crystal, and the aspect ratio will be about 1,000. And each silver nanowire will be 100 nanometer. So you can see this is an element mapping system. So you can see this is the silver, and the green part is gold. So you can see the gold is fully covered by the silver nanowire. So we also test the oxidation test by H2O2. So without any gold coating, you can see the silver is already oxidized. But by gold coating, there is no oxidase with H2O2 And after the DSC test, so you can see our material, the TG point, the melting point is surrounding by the 45 degree. So that's means the sensing range will be 25 to the 55. It's quite sensitive because when the PG melting, they will put more closer. The distance between two silver nanowire will be very close by the collaborative force. Then the conductance will increase. So we can measure the temperature. When the temperature increase, the resistance also different. So you can see the delta R by R. This is quite sensitive by the 20 degree to the 40 degree. This part is very good for the human temperature, human body temperature. So, and from the SEM picture, you can see the silver nanowire is coating with the PEG. So this is why our sensor is so sensitive. So we can attach our sensor onto the skin and we can measure the resistance. We also can measure in the water when you're sweating. So I think we can give you a video to show that our sensor is really, really sensitive. So we put on the sensor onto the lamp. So you can see when the lamp is shining onto the sensor, you can see the resistance is decreased rapidly. So that means when the temperature increase, the resistance will decrease very rapidly. So that means this sensor is really sensitive. Okay. Okay. So the next, I think the next will be go to the strength sensor. So the strength sensor, we try to develop a stretchable strength sensor for monitoring our breathing. So in our lab, we still using the silver nanowire, but we try to increase the conductivity of the sensing material. So we also add the silver nanoflips. So with silver nanowire and the nanoflips into the PU, then we can assembling this sensing material by packaging by this 2 PU tab. And we also use a magnet to use as the electrode. So later on, we just use the magnet and then we can very easily to extract the signal. So in the SEM picture, you can see the nanoflakes and then silver nanowire very clearly. So, so without any nanomaterial, you can see the PU will be stretched about 100 times. So the strength will be 1,000. But after we add the silver nanomaterial, 40%, 50%, and 60 and 70. So you can see the 70%, the mechanical property will be there will be changed a lot. Strength will be reduced a lot. In our electrical measurement, so within the 0 to 20% strength. So within this deformation, 50% is the performance is the best. So later on, we use the 50% mixing ratio for our test. We also test the repeatability. So you can see the over 10,000 cycle is very stable. The relative error only 2.7%. So our gauge factor is quite high compared to the other literature. So you can see the gauge factor will goes to 30. That means our sensor is very sensitive. So we put this sensor onto the human skin, especially in the stomach position, and then we can extract the breathing data. Looks like this. So you can see the upside, up and down, the frequency and the amplitude. We also can monitor this, and we can extract this data by human tests. So this video is taken by when a student doing the breathing test. So we can extract the data looks like this. And also we try to compare with the commercial measurements. So measurement instrument. So you can see this is the flow meter. We call it peak flow meter. So student, they just blow the peak flow meter, and we also attach the sensor onto the stomach, and we can extract the signal. After we have a theoretical inverse to the flow, the volume, then we can have this data. And the Pearson ratio is about 90%. So that means our sensor is really sensitive for the same with the result. So So right now we already approve the conceptual feasibility study. I think in the future, we will use this sensor to convert to the respiratory function, like how much volume you can breathe, this kind of things, and the speed. Okay, so we try to use this sensor to replace the bulky machine in the future. And I think this also need AI calculation because everyone has different size, different height. So we need to collect all kinds of data. So this is for 3 years project, and this year is the first year. So we will continue for that. And the last part of my talk is we also develop an e-textile. So the e-textile, we try to use the PVDF fiber. And this PVD fiber is using an electrospinning machine. So we designed this electrospinning machine. We have 10 nozzles, and we can use rotation to collect the sheet of the PVDF fiber. And all this PVDF fiber, we doping the CNT inside. So we have carbon nanotube inside the PVDF machine, PVDF fiber. And then student woven this PVDF fiber with normal nano nail clothes. So you can see this is the final product, and we can collect the signal by this electrode. So I would show the video. So if we tapping this clothes, the e-textile, so you can see the signal from in the desktop. If we put this into our shoes, we also can generate the electrode just when you're walking. If you try to do some exercise and your clothes also have this device, and you also can collect the power. So why I need to say this? Because the power is the most critical issue for the wearable device. So in the future, I think we can integrate these two device. We have the power generator, we have sensor, so we can so-called a cell power sensor. Okay. So for my talk for this section, I think decentralized healthcare is the future. So people, the centralized medical center, they will treat for very severe problem or cancer treatment in the future. But for the sub-healthy or health people, they will diagnosis at home. So point of care testing, biosensor, and the biomedical device are urgent need for the decentralized healthcare. And in our lab, we all doing the electrical sensing because that could be small size, lightweight, portable, and quantified and low cost. So that's also the advantage in Taiwan, because in Taiwan, we have very strong IC, IT infrastructure. So we can easily integrate with industry. And the nanomaterial enable a variety of the biosensor and the flexible electronics, and they can enhance their sensitivity as well as the specificity. So cell power AIoT sensor is the key because you need the data, and the data always coming from the sensor. So that's why our lab is focused on this topic. So sensor makes things smarter in the age of AI. I think the sensor issue is very important. So I want to thank my lab. So you can see our student, and it's beautiful beach here. And if you have a question, maybe I can take few questions after the talk. Okay, so later on, I would introduce a little bit about our so please wait, okay? So later on, I will introduce about a little bit about our program. Okay, so National Sun Yat-sen University, we have an international PhD program for science. Okay, so we call the IPPS. So actually, there is two MIT University in our lab. They all go through from this program. Okay, so this program, I think is interdisciplinary research. So you can go to the physics group, chemistry group, mathematics group, and the biomedical group. So our institute is medical science and technology group. Okay. So students, when they come to our university, we will have many activity to make this student, foreigner student, study like home. So you can see that Amy is here. Amy is my student, and he is also from the MIT University. And we also have some internship opportunity for the foreigner student. So the scholarship, I think we have a tuition waive for 3 years. And we also have the scholarship for per month is 15,000 per month. I think 15,000 is quite enough if you want to live in the Kaohsiung city. And if you try to apply for higher scholarship, you can go to Taiwan Scholar. And this is from Taiwan government, is 30,000 per month. Okay, so there is two apply season. Okay, so actually tomorrow, the September 30 is the last day for the spring admission. So I don't think you guys can match the deadline. So I will propose for the next year. So the next year is March 31, and is for the fall admission. Okay. So there is few steps. So after you apply, and we will do the review, and the admission notified will be June, and you will be on board about September. Okay. So if you want to know everything, you can just use this QR code. Then you can download the full information. I think the COVID-19 pandemic in Taiwan still, we have a very strong border control. So you need to know the border control. And I just want to know there is the 14 days quarantine in Taiwan. So before you come to Taiwan, you need to reserve the quarantine hotel and the border quarantine. And you need to make sure your flight. And there is a 14 days quarantine and a 7 days self-health measurement. Okay. So another one is I want to share our institute. So maybe, so this is our institute. And I will go through very rapidly. So you can see this is the Sun Yat-sen University, and this is the Kaohsiung Harbor. And we have the Xiziwan Beach in our campus. So our campus is really beautiful. So Institute of Medical Science and Technology, we established in 2013. And we have a very good facility here. And we already have PhD. So if you apply for the PhD program for the science, you also can individual apply for our institute. So it's parallel okay. In our institute, we have a professor. Okay, I'm the director of this institute. So my specialty is electrochemical sensor and flexible wearable electronics. And Professor Yang he is doing the microneedle and the biosensor as well. And Professor Liao, she is doing the drug delivery and the bio-nanomaterial. Professor Fan is biophysics chemistry. So he is doing a single molecule image and protein and DNA interaction. Professor Chen, he is doing a structural biology. So he doing a lot of simulation tool for the protein or antibody interaction. And Professor Lin, he is specialized for the brain-computer interface. So in his lab, he doing a lot of the brain signal detection, especially for the motion detection. The Professor Li, actually, he is MD he also is a medical doctor. And his research is the clinical toxicology by using the mass spectrometer. And Professor Chen, he is doing the biomedical bone material. So it's ceramic base. So in her lab, they are trying to synthesize nano ceramic for the bone material. Okay, so I will gonna very quickly go through our professor. So you can see this is, I already told you about my research, and we doing the biosensor and lot of patch type sensor. And Professor Yang is doing the microneedle and also this kind of, for instance, nanomaterial for the virus detection. Actually, he also start up a company for the COVID-19 detection. And Professor Liao is doing the like a photo-induced nanomaterial for the cancer treatment. And Professor Fan, he has his own developed the optical detection method for the single DNA or single molecule detection in her lab. Professor Chen is doing a molecular simulation tool for the protein-protein interaction. He also developed the database method for this research. And Professor Lin is doing the brain signal detection. So they developing this kind of EEG, so you can see the brain-computer interface. And he also doing some motion control for the brain signal. And Professor Li is doing the mass spectroscopy for the for the hospital use. And Professor Chen is doing ceramic, nano-ceramic material for doing the bone synthesis. Okay. So I think our university also, so you can see your university is here, and we already signed an MOU with many foreign countries, and we also have very international, we also provide an English talk class in our institute. And we also collaborate with many hospitals in Kaohsiung area. So I think we can have the PhD degree and the master degree. Okay, so this is our overall research performance, and I think our professor every year maybe publish over 4 to 5 papers for different journals, and I think that these are the very high-ranking journals. So I just want to show this introduction. So later I will give the two. So give me more 5 minutes, okay? So I will show you our lab.
Grammarly does more than catch errors. With Grammarly, you can find.
So this is the introduction video of our lab. So you can see this is the student office. Okay. And then this is our lab. So the student office is separate with lab. So we have many test platforms here, and we have 3 batches. And we also have a yellow room for the photolithography. So we have the electrochemical analyze and force. These are all the equipment in our lab. We also have our own conference room. And this is for the electrochemical sensor. So students can synthesize their own material and test the sensor by the electrochemical station. So I already introduced about our research. This sensor is for the pressure sensor. So we use the polymer with carbon tube, so we can do the smart shoes, and we can know the force applied on the shoes. All the sensors are fabricated in our lab. This is stretchable sensor. So we can monitor the breathing, and we use the nanomaterial to do the sensor. This part is for the temperature sensor. We also use the hydrogel to do the sensing. So you can see it's quite stable, and we also add the silver nanowire into the hydrogel. So we have many PhD students and international students here. Okay. Okay, so I think I stop here.
各位曲博科技教室的观众朋友，大家好，我是曲博。各位知道呢，3D 列印发展了已经超过了20年的时间，但是呢，因为3D 列印一直没有办法突破。
Okay.
Okay, thank you very much, Professor Cheng, for sharing your profound knowledge with us. So I request participants, if they have any queries related to the topic of your talk, and it can be about PhD program, they can discuss it with you.
Yes, welcome. So maybe you can share my email, then they can send the email to me.
Okay, Professor Cheng, no problem. And I think because of shortage of time, we can't discuss queries right now because you have other commitments also.
Yeah. I need to hurry up.
We can do one more thing also. The participants can share their queries in the chat box, and you can try to reply as soon as possible whenever.
Sure. Okay.
Okay.
No problem.
Okay, so it was a great session full of useful information, and we rarely get this kind of opportunity to listen to the words of a great knowledgeable person like you, Professor Cheng. So thank you very much for sparing your time with us and for sharing such a great knowledge with us. Thank you very much.
See you.
Okay. So now the next distinguished speaker to honor us presence is Professor S.K. Sharma from JNU Delhi. And Professor Sharma is currently a professor and director of University Science Instrumentation Center, JNU New Delhi. He has already worked as scientist with DRDO, director and advisor in All India Council for Technical Education, Ministry of HRD, and founder director at Advanced Instrumentation and Research Facility at JNU Delhi. The areas of his research interest include atomic and nuclear radiation physics, XRF, electron microscopy, and characterization of nanomaterials, etc. He has authored and edited around 12 books in physics and many research papers, about more than 100 in the international journals of high repute. He has more than 35 years of experience in teaching, and he is a member of many scientific societies also. So with a long list of his achievements and glory, I would like to invite Professor Shetendra Kumar Sharma. Sir, please put a light on the topic of your talk, applications of UV spectroscopy. So over to you, sir.
Thank you, Jyotsna. I am very thankful. Are you able to hear my voice?
Yes, sir, you are audible.
So I am very thankful to Dr. Jyotsna and Dr. Yadav for giving me this opportunity to share a informative talk for the layman users on the UV visible spectrophotometry. So this is an introductory talk. I share my presentation with you. So just hold on. Let me. Let me share my screen. So are you able to see my screen?
Yes, sir.
Okay.
Screen is visible.
Screen is visible. Okay. So this is my topic, application of UV visible spectroscopy for material characterization. In this talk, I'll just introduce new researchers about that one of the characterization technique, very simple, that is making use of UV and visible spectroscopy. Okay. So it will be an introductory lecture because most of the students who start their research career, this is the very simple and very popular instrument which is used for characterization of the materials. So first of all, we just have a look at the characterization technique which are very commonly available in the research lab. The first one is UV visible spectroscopy. Then you have Fourier transform IR and Fourier transform IR and Raman spectroscopy. Powder X-ray diffraction, that is called XRD. Electron microscopies like SEM, TEM, HR, TEM, etc. Then scanning probe microscopies like AFM and SPM, and small angle scattering X-rays, X-ray fluorescence techniques, energy dispersive as well as wavelength dispersive. Then X-ray photoelectron spectroscopy called XPS, photoluminescence spectroscopy, Raman spectroscopy, magnetic characterization, and there are many other you can say subcategories of these techniques which are applicable to different type of samples, because For biological samples, some different technique is used. For material science, some different technique are used. Okay, so these are the general list of the techniques. But as you know, the spectroscopy is a broad field with many sub-disciplines which can be classified by the type of material that is being analyzed. So this is mainly related to molecular spectroscopy, which we discuss here under UV visible. So basically we see here that atoms, for atomic analysis, you have atomic spectroscopy, these ICP and MP, AES, AAS, etc. So these are the techniques. For molecules, you have visible and UV spectroscopy and visible near IR, FTIR, and fluorescence spectroscopy. For investigating the crystal structures, we have X-ray crystallography. For nuclei, we have NMR, etc. Okay, these are the classification based upon their nature. So every molecule has some kind of fundamental vibrations associated with them, whether it is a water molecule or any other molecule. It has some kind of natural vibrations associated with it. So those vibrations here, I have shown three types of vibrations that are possible in water molecules. So like this, every vibration has a characteristic. When you have a wavelength interacting with the molecule, that is in resonance with that particular vibrational frequency, then it will absorb that particular radiation, or it will emit that particular radiation at a particular wavelength. So that is the basis of use of this UV visible spectroscopy. Okay, so here we can see that molecular absorption takes place because the ultraviolet and visible light, they interact with valence electrons, and their energy range or the wavelength range of interaction is around 200 nanometer to 700 nanometers. So that is the range of interest of UV and visible spectroscopy. Then we have infrared and Raman spectroscopies. They are also related to the molecular vibrations, but their range of interaction is 100 this centimeter square is the wave number, because that is the wave number is the normal unit that is used in Raman spectroscopy. That's why it is written. But otherwise, you can see that it is 0.7 to 50 micrometer is the range. Then we have nuclear magnetic resonance, NMR. So for that, you have a frequency range of the RF waves from 100 megahertz to 1 gigahertz. Then where this UV visible spectroscopy is used, it is very simple technique and it is inexpensive, and it is applicable for many different but not too complex samples, because it gives the very simple data at the output. For complex samples, we have other techniques like GCMS and other X-ray techniques. So it is used for routine measurements for hospitals, petrochemical industry, food industry, water quality control, because it gives a rough idea about the samples immediately. It just takes 5 minutes or 2 minutes to record one spectrum and you get a rough idea what it is. Okay, that's why it is very popular technique that is in use in universities, chemical and biological plants, because in process plants also, when some chemicals are being produced, during the batch processing, this UV visible spectroscopy is also used. And you know that UV and visible spectrum, they are just a part of very large electromagnetic spectrums. And UV range lies from 190 to 400 nanometer. Visible range is from 400 to 800 nanometer. And infrared wavelengths, they vary from 800 to around 100,000 nanometers. Okay, so these are the range, and the normal or popularly available models of the UV visible spectrophotometer. The range is written as 200 to 1100 nanometer. because instead of 190, they start from 200, and instead of going only up to 800 nanometer, they go up to 1100 nanometer. Okay, that is the normal standard available. And this is our electromagnetic spectrum that you can see, that where our ultraviolet and infrared regions they lie. And this slide shows you that in what frequency range, what are the vibrational range or the absorption range lies. For example, ionization of atoms and molecules, they take place in the inner shell electrons or valence electron. So they range from 1 nanometer to 200 nanometers. And similarly, the molecular vibrations, they start from around, say, it may be, say, 1 micron to around, say, 100 micron. Okay, so that is the range you have to see. And the most important thing is that the color, when you form a sample, the sample may be a particle, a powder form, or it may be in the form of a solution. First information we get is from the color of the sample, because when we look at the color of the sample, we just guess that what is the nature of this material which we have formed. Because when you dissolve those particles in solution, maybe of ethyl alcohol, benzene, or water, then you shake it and look against the sunlight, then it will show you some color. If that sample is completely black, it means it is absorbing all the radiation, and no radiation is allowed to pass through it. Okay, and nothing is being reflected also. So color becomes a very important property. It gives you an idea about the size of the particles that solution contains. Okay, so if there is a um, red solution in a test tube, then you can immediately guess that the wavelength that is being reflected or transmitted through that solution is in the red region, and rest are being absorbed. Okay, so that gives you a idea of the size, that all the wavelengths which are shorter than red, they are being absorbed, means the size is of that particular order, of the order of the wavelength of the uh, uh, light that is being absorbed. Okay, so with that, we have a rough idea. So here is a color and wavelength, you can say, um, matching chart is given here. So you can see that wavelength of, say, this order will show you the red color, and complementary color is blue-green. Absorbed color is red. It means that if in transmission you will see, it will be blue-green color. Okay, so for this particular wavelength, this kind of color will be seen. So absorbed color and complementary color means the one which is reflected and one which is transmitted. Okay, so that is a rough idea, that colors also give you a rough idea. In case of UV visible spectroscopy, what we do, we make use of a light source, that is the lamp, that emits light in a range of a broad range of wavelength. Then we make use of a monochromator, that is a dispersion device that can be a grating or a kind of prism to select the wavelength. Then we have a sample area where we put our sample, and then we have a detector that detects the uh, strength of that transmitted light or intensity of that transmitted light, that is measured by a detector. And concentration is determined by comparison with the standard data that we store for our record. Okay, so this UV and visible or IR spectroscopy gives an information about the size, shape, concentration, agglomeration, refractive index, etc. These are the properties that are the that can be inferred out of this data. And that makes UV visible IR spectroscopy as valuable tool for identifying characterizing and studying these materials. And nanoparticles made from certain materials such as gold and silver interact with specific wavelengths, and they have some unique properties that you can identify the size or the shape of the particles. Okay, so these uh, spectrometers or this technique is used in various kind of analysis like DNA, RNA analysis, pharmaceutical analysis, when you formulate the drugs and say medicines. Then bacterial culture, you can uh, keep on monitoring the bacterial growth in the solution. Then beverage analysis, because when you uh, uh, brew the beer or whiskey in a brewery, then the process analysis can be investigated. After particular time, you can check what is the state of brewing. Okay, and other chemical application, laboratory applications I have already mentioned. And analytes that can be dissolved in solvents like water, ethanol, and hexane, they can be analyzed. But analytes need to absorb UV or visible light. That is the precondition. Because if some material is neither absorbing UV or visible light, that will not give any information, because for that no interaction between incident light and the sample is taking place. So you will not be able to infer anything out of the result. And this technique is can give you the quantitative measurement also. And also you can analyze more than one analytes in the solution, provided they do not interfere with each other. Analytes that have a photochemical reaction at wavelength range of interest, that is not suitable. And unclear or colloidal samples, it is not suitable, because if there is a colloidal solution and it absorbs all the radiation coming, and nothing is transmitted through that sample, so detector will not record anything, so it is not suitable for that. One simple method is that blood serum or urine, they are analyzed by our these uh, so-called test labs or path labs, is by using a spectrophotometer, because they detect the amount of albumin and amount of sugar in your blood just by looking at the UV visible spectroscopy results, and that curves are, they indicate if there is a sugar there or not. So how they look like? There are hundreds of models, rather thousands of the models are available in market. Different labs have different shapes of the instrument. So you may have any of these kinds of the spectrometers in your lab, and you need not to be confused, because in old days these instruments were without any LCD or digital controls, and they used to plot graph using a pen. But now everything is digital and everything is miniaturized, and you can have a very small size spectrometers. And now the latest one are on with the laser. That laser based UV visible spectrophotometers are so small that they are not of this size. They are, say, handheld kind of devices that you can just have a cuvette, and there is this optical fiber that is you can put around that cuvette, and on the other side is a detector. So it is a handheld portable device that is a spectrophotometer. So you need not to worry about what is the shape and body looks like and what are the units, but the results are almost identical unless it is a very specialized instrument. Okay, so the basic technique is very simple, that you have a beam of light I naught that passes through this cuvette that contains a solution, and I intensity comes out of it, and that is the principle, and it absorbs some intensity is absorbed in the solution. Okay, so let us have a look at the components of the spectrometer. So you have a source, then dispersion device, and then sample holder, and then another detector to detect the radiation. So this is a schematic of single beam spectrophotometer. So these spectrophotometers can be of single beam or two beam type. So if it is a single beam spectrophotometer, then we have only one place for the sample, that only one cuvette position is there. That once we have a say solvent or there to record the baseline or to record the zero spectrum, then you have to replace it with sample again. You have to record two type of spectrum, first with the blank sample and another with the real sample, and then you have to subtract the real sample, this blank sample from the real sample, and then you get the result of that those particles which are there in the sample. But in order to minimize that hassle, now the companies make dual beam spectrophotometers that look like this. So here the same beam of the light is splitted into two parts, and one is passed through the reference sample and then another through the actual sample, and two identical detectors are there. So that gives you an advantage that you need not to change the sample again, and the final spectrum is recorded at once. Okay. So the zero baseline is recorded by putting the same solvent in both the cuvettes. So first we record a zero spectrum. We put either water in both sample or ethanol in both samples or benzene in both samples. So so that the solvent effect is not there. The effect our detector records is the effect of those particle that is available only in sample cuvette. Okay. And then we have a special light source. That light source should be ideal light source, should be a single one that covers the full range, whole range of the UV to visible. But in fact, there is not a single source available that covers whole range. So that's why two different type of lamps are used. That deuterium arc lamp is used, that is that covers the UV region, and then tungsten halogen lamp that covers the some part of UV and then entire visible range. Okay. So, and add the xenon lamp that is good continuum over the entire UV and visible range. But xenon lamps have very limited life. So, and they are very costly also, and they are their life is too small. So we generally avoid these, but some old machines, they still make use of xenon lamps. But most of the portable spectrophotometers, they have this arc lamp as well as this tungsten halogen lamps. Okay, so this is how dispersion device works. So dispersion, as you know, is splitting of light into its components. So prism is one of the simplest dispersion device, but instead of prism, we make use of gratings. So you might have studied in your BSc courses that gratings are used to uh, uh, work like prism. So they also split light into different parts, and gratings are very rugged. They occupy very small space, and you can lightweight, you can put them on a stage that you can rotate, and then you can record the spectrum. So ideally, our wavelengths should be separated like this. On the left side, you see the two vertical lines. They are basically ideal output peaks that are fully resolved. So my spectrum should look like this, but practically it is not so, because the detectors that are in use or that are put in the instrument, they have a limited resolution. For due to their limited resolution, the outer peaks, they will appear like this. The position of these two peaks will tell us the position of these two wavelength. So that is a limitation that you must understand, that whatever efficient instruments may be, its quality of output will be limited by the quality of components that are used, and the components are never perfect. So our spectrum output will be compromised in many ways. Okay. So now we prepare the sample. If the sample are solution, use at least 1 ml of your sample for measurement in standard quartz cuvette. Solvent is usually ethyl alcohol or water, and it is used to disperse in the material to measure the background, means the noise, or you can say reference kind of a thing. And the dilution of the sample may need to optimize after observing the rough peaks. Sometimes if you take very concentrated solution, then your peaks may overshoot the y-axis. So you need to dilute the solution so that you can see the peaks. And the sample suspension may need some sonication or vortexing. Why? Because sometimes your uh, particles are so heavy that they settle down immediately on the inside that cuvette. So for a better recording of the spectrum, they must be floating in the solution like a colloidal solution. So unless there are particles in the path of the beam, so nothing will be observed. So it will be a spectrum corresponding to the solvent only. So we need to sonicate it so that all the particles, they are uniformly dispersed in the solution. Then we have, for recording the spectrum, what we have to do first is we have to calibrate the baseline, take some solvent in both the cuvettes, record the spectrum in the range of interest. And for recording the spectrum, we put the test sample in one of the cuvette and repeat the same scan. And colloidal solution sonication may be required. Okay. So the type of spectrum which you will see is like this. On x-axis is the wavelength, on y-axis is the strength, this intensity or absorbance or transmittance. So whatever parameter you are measuring, and these days these computerized UV spectrophotometers, they have built-in software. So by using the software, you can choose absorbance versus wavelength, transmittance versus wavelength, or time versus intensity. Whatever you want to record, you can record. Okay. So what is transmittance and absorbance? So that is understood that amount of light that is absorbed by the solution depends upon concentration. Higher is the concentration, less will be the path length of light, and it will be absorbed in the cuvette. Similarly, the transmittance is the ratio I divided by I naught is the indication of concentration of the analyte in the sample, and it is defined as transmittance or represented as T. Okay. So if there is no absorption of light, we can say that transmittance is 100%. But most popularly used item in UV visible spectrometry is absorbance, not the transmittance. And absorbance is defined as A is equal to minus log to the base 10 T, and it is equal to T equal to minus log to the base 10 is the ratio of I to I naught. Okay. So this is the and absorbance is also related to uh, 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 this Beers-Lambert law. So A is absorbance, here C, D and alpha, they are defined below, that sample thickness, absorbent concentration, absorption coefficient, they are there. And reflectivity is also related to, is sometimes used in uh, this spectrometry, but that is not very commonly used. And concentration of the material in the cuvette sample, that is also can be calibrated with the absorbance, because absorbance, if you plot with the concentration, then you can have a calibration curve. And if you want to measure the unknown concentration of a sample, that you can determine after calibrating your spectrometer with this type of peak. And if you, this is a kind of a sample graph I have taken from internet just to show you that how concentration can increase. You see this top one blank, it is the blank line is the horizontal line here, that once it is blank then it means it is horizontal. uh, this is the baseline. Okay, if at 5 micromolar concentration, this is the peak. As the concentration increases, you see the first peak and this most prominent peak both increase in intensity. So you can calibrate their intensity values versus their concentration, then you can determine the concentration. So this type of change in curve shape will be visible to you with the change in concentration. Okay, and you can also analyze the mixtures also. Instead of one material in your solution, you can have more than one material, but they should have different molar absorptivity constant, and you can also measure these two different materials. For example, here different colors of the curves are shown to you. So you can see that one particular red chemical is having a red peak, this blue one is having a blue peak. But if they overlap, somehow if they overlap completely with each other, then this technique may not work. But if they do not overlap, then you can determine the concentration of all components using this technique. Okay. And purity analysis and kinetics analysis. So kinetics means that with time, how these concentrations are changing. So you can see that characteristics of these chemicals or some reaction that is taking place in the cuvette with time, that you can observe here at 0 minute some peak is there. As time passes through, then different these peaks are there. So you at the bottom you can see 18 minutes. So the red one is the 18 minutes. So after 18 minutes, your curve becomes like this. It means whatever chemicals were present here showing high peak, they tend to disappear with time. So they reduce and they disappear, and your curve becomes smooth like this. Okay. So there are different settings in modern UV spectrometers that you need not to manually set it. After given time, after every 4 minutes, for example, or after every 2 minutes, they will record a spectrum for you without manual intervention. You can set it at auto. So they will record spectrum after repeated intervals. So that will give you a set of so many curves, and those you can superimpose upon each other, and you can generate this type of a graph. So this is again a catalyzed reduction of methyl orange. So you say using some catalysis. The methyl orange, that is a dye, very commonly used dye. So with the time, you see this peak will go up, peak at 250 nanometer goes up, and this peak at 464 nanometer goes down. And this graph you can generate using UV visible spectrometer. So that gives you an idea what is happening to the chemical with time. So that change in time. So for example, if you want to stop the reaction, so at what time your reaction should stop, or at what time another additive should be added to uh, achieve the next reaction, so that you can immediately get from this type of curves. And that's why it is very popular technique that is used in chemical process industry, because it is a very cheap and very simple technique that gives you a idea. This is a sample of absorption of liquid water spectrum. Why I am showing it? This is a UV visible spectrometer, that graph. It shows that there is a very low absorption in this range, say around 14 nanometer or something like that. So this is one, so it may be something around 20 nanometer or 14 nanometer. So it means that if you have some kind of wavelength in this region working, or a communication system working on in this range, that will be least affected by clouds or rains in the sky, because it will be absorbed minimum. Okay. And another interesting thing is that absorbance in the UV region is very high, 10 of the order of 10 raised to power 8 or 10 raised to power 7. It means that most of the UV wavelengths will be absorbed by water. It means if you make use of water on your body, then you can protect yourself from UV burning. If you are likely to be exposed by UV radiation, it is better to be wet, have a layer of water on your body, then you can save your skin from UV burning. Okay, that is a very simple case. Then we have transmittance and path length. There is a Lambert law. This curve is nothing but a transmission and path length, means that mathematical formulation of this T is equal to I by I naught is this type of measurement we can also plot, that how the transmission changes with the thickness of the sample or the length of the sample, that you can observe. And concentration also similarly, the transmission, as you change the concentration, the same type of trend will be there. And how to interpret your data, that on the left side is the absorbance, on the right side is the transmission spectrum. They are not exactly opposite of each other, because sometimes we feel that absorbance is different, is opposite to transmission. So you can just invert the y-axis of the left curve, so that will give you the transmission, because that log to the base 10 is involved. So that's why transmission curve is slightly different from the absorbance curve. Then scattering and absorption. So here is again, it is gold nanoparticles. You see there is a this type of brown color visible, and that you can see that it is a because light is absorbed across the entire visible spectrum except this. So only these wavelengths are allowed to pass, rest wavelengths are absorbed. And another, this is a silica colloidal solution. So here all this Rayleigh scattering scatters almost all the wavelengths. So that's why we find the color to be white. Okay, so that is the difference. And then you have contribution of scattering and absorption. So you see total extension is there, optical density is there. How they combine, and the total extension of this optical density is like this, so that you can find. And aggregation effects are also there. The way I told you that how with time we record the spectrum. So it is a with time aggregation is taking place in the solution, means some kind of precipitation is taking place, because when there is a clear solution initially, like we form the cheese in cottage cheese from the milk. So as the milk particles, they start combining with each other to form the particles of the cheese. So it means there is an aggregation taking place, and the size of those particles is increasing. So the color of that solution will change from one color to the other color depending upon the size. So here you can find that at 0 minute means the topmost curve. So as time passes, this curve goes down, but the peak at the bottom also appears. This red one appears, then these uh, blue ones and this magenta curves, they also appear here. So second peak appears here and this peak comes down. So it means one thing is reducing, another thing is being produced. So that effect can be investigated in using this simple technique. And there are some strengths of this is that it is a non-destructive technique. It means the sample is available with you. You can reuse it for further processing. Your sample is not destroyed. And another is measurements can be performed very quickly. Little user training is needed because instrument is easy to use or handle, and only minimal processing is required for data analysis. And instrument is not costly. It costs few lakhs only, so that you can use. And I think it is all about introductory part. And now I'll show you some video as a demo on actual instrument I have used. Just hold on. Well, here we have a spectrophotometer of analytical company that has a electronic control unit on the side. Are you able to see it? Display on the top.
Sir, the video is not visible. Please share it again.
Is the sample chamber. Let me open this sample chamber. You will find.
First open your video, then share your file.
Well, here we have a spectrophotometer of analytical company that has a electronic control unit on the side with a LED display on the top, and the black portion that you are looking is the
Yes, sir. Now screen is visible.
Let me open this sample chamber. This is visible?
Yes, sir.
Okay, I'll restart it.
Okay.
Well, here we have a spectrophotometer of analytical company that has a electronic control unit on the side with a LED display on the top, and the black portion which you are looking is the sample chamber. Let me open this sample chamber. You will find there are two cuvette slots available here. One is this one, another is this one. So one of them is the sample cuvette and another is the standard sample for the comparison. For example, if you want to take the UV spectrum of copper sulfate solution in water, then in one of the cuvette you will have water as the sample, and in another you will have the copper sulfate solution in water. But if solution is in ethanol, then the standard sample or the comparison sample will be pure ethanol, and your sample to be analyzed will be made in ethanol as a solvent. Okay, so these are the two major parts, and the beam comes from this side and passes through this cuvette to this side, and here is the detector. As I have told you in the theory part, detector is placed here. Here the second detector is here. Okay, the source is here, and for this source is here. But for these two beams, they are created from the same source, so that the identical wavelengths are passing through, and the detectors are also identical. But for the purpose of testing, because with time
one detector may change its property, but other may not change. So what we do, we take a baseline. That means the reference line. First, we will put water as a sample in both the chambers, and then record our spectrum to take the baseline just to check whether our both detectors and both transmission paths are identical, because there may be some difference in the cuvettes also, because one cuvette may have thicker wall, sometimes finger prints are there on the cuvette. So for that purpose, we take a precaution that we do not touch the cuvettes with the bare hands, but we make use of gloves so that our fingerprints are not printed on the cuvettes, because quartz cuvettes, they are very sensitive to fingerprints because a lot of radiation gets reflected back. Okay, so now let us switch it on to show you how the spectrophotometer works. So let me close it, and then I have a switch of power switch on the back. I switch it on and I see the display coming. So here is the display starting. Every spectrophotometer has different settings. Okay, so you need not to worry about what are the graphic user interface and how things are there. So now it is doing the self test. So what it is reading, it is checking the lamp motor, that is passed, means lamp is motor is working fine. Grating motor, it is checking, and filter motor, slit motor, tungsten lamp, neutron lamp, and wavelength check, and initialization parameters. Last one is the parameters that we have set. Okay, so if we have not set any other parameter, then it will not check it. But all these parameters it will check, and then it will say that everything is okay. So let us wait till it checks all parameters of the spectrometer under self check. And here are the keys and buttons to select some certain things, like this run and auto zero, and this is the dial by which you can change this cursors, move cursor left and right, and this is the button which you can press and say it is something like enter in the computer keyboard, that you just execute that particular thing. Okay, so this is for the start also. You can press this button to start it. And different spectrometer of different companies, they have different user interface, and different things will be visible for you. But you have to read the manual of the instrument, understand it's working properly, then operate it. Okay, so now you see all these parameters are in green. So it means all things are okay. So, but wavelength check is also passed. It means it is okay, and initial parameters it is checking because it wants to check if you have given some initialization parameters. If you have not given, then it will use its own standard one, which are fed into the memory of this software of the instrument. And once they are okay, then it will come to the measurement mode. And this instrument is connected by using a USB cable. You see, this is a USB cable that is connecting this instrument to the computer. So there is a computer CPU, it is connected to the computer CPU, and here is the computer on which it is connected. So let me show it how the software is uh, there for this instrument. So let us see, find it out. So this company is the Analytical. So under Analytical, there is a software. So here you find the Spectra UV. and user guide is also loaded there with this, and there is a icon for uninstalling this software, but we have to run this software Spectra UV. So we click this and we start this software, and you will find that this software is loaded. So it is already started. It is already started, and you find that user interface of this machine is loaded, and it has all the measurement parameters set. The default is the absorption spectrometer mode. Then T is percentage is transmission. Then ES and ER are the reaction rate and other scan parameters. And scan interval is given that wavelength in nanometer step, that 1 nanometer in one step. So it can be faster. You can choose it 2 or 5 if you want to do faster analysis. But faster analysis will not give you the details of the spectrum. So for finer details, you can have it minimum as 0.05. Okay. So first of all, you have to understand what this software does, and you find that there is a method. Method means that you have to first give the method to what method you want to follow. Okay, so let us say new method. So new method means that a new method has to be there. Or you can say open. Open means if you already have some spectra and you have given some parameters or settings, then you can use it. Or you can create some settings. Chroma means that the display, how you want things to display. So you need not to change it, but spectrum control and method, you can change it. Okay. So spectrum control is there, method you can choose, and new method we have to find out. Okay. Scan parameters you can give, say I give it as 2 and say okay. So this is a parameter and which I can give the sample ID. Sample is, say, for example, here we have cuvettes. Well, here we have cuvettes. These are quartz cuvettes, and these have two grounded faces, which are not to be used for transmission purposes. So the sample has to be placed in such a way that these transparent faces are towards the beam, so that beam transmits properly, and these are grounded so that no stray light can enter. So these are two identical cuvettes made by same company and of the same size and shape and thickness, so that identical phenomena takes place. So before starting our real experiment, we have to record the test samples or kind of a baseline. Okay, so first we will put water in both the sample, because we have prepared this potassium dichromate solution in water. So this solution has to be in the same solvent in the standard sample or the reference sample, or in the under the test sample. So that effect of solvent is not there. Okay. So we have put the two cuvettes. One is under reference sample, and this is for the test sample. So both cuvettes are having DI water, deionized water, and we will test them. Okay. And then we have clicked the start button for the spectrum. So our start wavelength is 1100 and wavelength is 200. Now you can, what you can do, you can just change this to 800. So you can type, press 800, so and enter. So this becomes 800, and end wavelength I want 400, so it becomes 400. So enter, and y minimum and y maximum is 1 volt. Scan speed is fast, and scan step is 1 nanometer. So if I want, I can make it 2 nanometer per step, or up to 5 nanometer I can go. So let me make it as 2 nanometer. So I make it selected 2 and then press it, save, and then I say run. Okay, so now the spectrum is being recorded. So you see it displays there on the instrument also, and as well as on the computer also. So you see there is a magenta line coming, so that indicates that some reference spectrum is being recorded. So this is the reference sample we have recorded. So one of them is of the Kuwait 1 and another is of the Kuwait 2. So they are slightly different. They are different because one Kuwait is having some fingerprints on it, and otherwise they should have been exactly identical. You see, in this green part is slightly above this magenta part, and here it is also again above the magenta part. Ideally, this should have been overlapping with this perfectly. Okay, then we say that both Kuwaits are having the identical. Before taking recording the spectrum, we have to set our method of recording. So we can set the parameters here, that it is a fast speed, wavelength step is to 1 nanometer. So let me make it 2 nanometer, and I say okay, and then I send this method for the computer to record, and then I create a baseline, or first let me see how the spectrum of the water sample in both the Kuwaits looks like. So I run it. So now you can see that the recording has started, and you will find a spectrum being plotted on the screen. That spectrum you can see on the both either on the spectrophotometer itself or on the computer screen. So on computer screen you see that its scanning has taking place from right to the left, because from higher wavelength side it is scanning towards the lower wavelength side, and you see some spectrum is being plotted. But you look at the scale of the measurement, it is the absorption, that is of the order of 0.001. So it is a very low absorption. So the peaks which you are looking is around zero line. Zero line is this line. So this is around 0. Okay, so it means there is a minor absorption, random absorption around 0.001% or of that particular order. So it means that reference and the standard sample Kuwaits are nearly same. So now we acquire the sample spectrum. So we stop this Now I have put the potassium dichromate solution, very light solution of potassium dichromate, and let us see how the spectrum looks like after this. So now you look at the scale of absorption. The scale has changed drastically. It is of the order of 10 raised to the power -6, and it is 500 or something. So now you see how the spectrum looks like. Let it be complete. So effect of potassium dichromate is now will become visible. If it is not proper, then we will change this spectrum again. We will change the concentration again. Okay, so this is the spectrum of absorption spectrum of potassium dichromate, very light solution. So let us make it more concentrated. Now we have changed the concentration of the sample, our standard sample, and we are now recording the spectrum again, and let us see how it looks like now. So when we started, so due to auto scale problem, the scale may not be looking good till the complete scan is over. So let us see how the spectrum is behaving now. You will find different type of peaks. Okay, so this is the spectrum of potassium dichromate that we have recorded. Okay, ये हमारा है, ठीक है, potassium dichromate का spectrum. So we are restarting the measurement because in our earlier experiment the concentration was too high, so we have diluted the solution and we are again running the same experimental measurement from 200 to 500 nanometers, and you are seeing the recording of the spectrum. We can compare this recording of the spectrum with that of the standard one which are available on the internet for potassium dichromate samples, and then we can guess whether our measurements are perfect or not, or whether our spectrophotometer calibration is okay or not. So that is the purpose of making use of a standard sample before going for unknown sample. So we record this sample and we say this is over, and we say okay. And so on right side you see this is the standard sample, and we can paste it on the this image on the standard page where we have already pasted a standard image of this UV visible spectrum for potassium dichromate. The top one is the standard one, and the bottom one is the spectrum that we have recorded. Okay, so with this method we can record the spectrum of unknown samples, and we can determine their concentration or absorbance or transmittance. There is a formula to convert absorbance into transmittance that we have already discussed in the theoretical part. So this is all about this, and the major precautions are that the sample has to be started with low concentration first, because high concentrations sometimes overshoot the measurement range of the spectrometer. So your spectrum may not be visible at all. So because it goes above the y-axis, so you may not see anything. So it is better to have recording starting from very low concentration of the sample, and it depends upon the material to material what concentration has to be used. So before using the spectrophotometer, make some study on the internet that what type of the spectrum it will be and at what concentration it should be recorded. Otherwise, you will waste a lot of time in hit and trial. Okay. Thank you. Any other question? I think it is over. Hello.
Thank you very much, sir. And I request participants to ask your queries. The session is open for questions. Sir, actually some participants have put their questions in the chat box.
Yeah, one question I have seen that nothing is coming in the spectrum. So I request her to look the last part of video, that concentration has to be very low first, and you keep on lowering the concentration. If the initial concentration of the solution is high, then all the peaks, they go above the y-axis. So nothing will be visible on the screen. So you will not find any spectrum. Okay, so first you try with low concentration, then keep on increasing the concentration and then see.
Any other questions? Sir, actually there are questions, but in the chat box. So
Okay.
you can reply there only. I think the participants are on mute. Okay, so we can
can you
end the session, I
read?
think.
Can you read, sir, may I come to JNU for these measurements? Yes, you are most welcome. What else is there? Any other question? I don't think any other question is there. If I am not
Okay.
able to read, you just read for me.
No, sir, there is no other question. So I request the participants once again to put your queries in the chat box. Sir will try to resolve all the queries or to reply as soon as possible. Okay. And we can end the session now. Thank you very much, sir. Your session was full of zeal and valuable information about UV spectroscopy. And the lab session was really very useful. And it surely helped the participants to understand the topic very well. Thanks a lot. And there is an announcement for the participants. Dear participants, a link will be shared for attendance and feedback after the last session of Dr. Neelam Kumari. And it's mandatory to attend the last session. And after filling up the attendance and feedback form, which will be given only at the end of the session, a certificate of participation will be generated. And so from there, you can get your certificate of participation automatically. So this is the time for a break. So we will be resumed back at 2 o'clock with our next distinguished guest speaker, Dr. Neelam Kumari. Thanks a lot.
Okay, thank you. Thank you, Dr. Joseph.
Thank you, sir.
Madam.
Hello, Dr. Neelam.
Hello, good afternoon.
Good afternoon, ma'am. How are you?
Fine, thank you.
Namaskar, madam.
Namaskar.
So, yes, sir. We can wait for some time.
Actually, अभी 2 o'clock हुआ नहीं, तो we can wait for more 3 minutes.
Yeah. Sure.
So should we start?
I think we can start.
You can just check the number of participants.
I think students are joining. It's the 28.
How many have joined?
It was like 110.
110.
Yeah.
So we can start, I think.
Yeah. I think we can get going.
Okay. So welcome back, participants. It will be a privilege for me to welcome and invite Dr. Neelam for her talk. And I really thank you very much, ma'am, for accepting our invitation for delivering the talk. And before the last session, I would like to invite Dr. Chandrasekhar to introduce Dr. Neelam. Over to you, sir.
Thank you, Dr. Joshua. It is really a privilege and honor to introduce Dr. Neelam as the speaker of the session. Dr. Neelam is currently working as a senior scientist at CSIU, CSIR Chandigarh. Dr. Neelam completed her MSc Physics from Punjab University, Chandigarh, and her PhD from Indian Institute of Science, Bangalore, before joining CSIU. Her area of expertise includes, but not limited to, vacuum deposition, optical thin films and coatings, optical characterization, avionics display, and cockpit instrumentation. The current area of research on which Dr. Neelam is working are optical film filter technologies for band pass, low pass, and high pass filters, design and simulation of optical coatings for foldable and flexible military grade optical substrate for see-through displays, and design and simulation for beam combiners, beam folders, and high reflection and anti-reflection coatings for taxi and landing application for fighter aircraft. Among the significant achievements that he has been involved in, the first one is the head-up display achieved a technology for light combat aircraft Tejas Mk1AF and LC Mk1 NP for Navy, and the development of state-of-the-art facility for optical thin films and characterization at CSIU Chandigarh. Dr. Neelam has won many awards in national and international conferences, including the Gold Storch Transformation Innovation Award 2017, which is considered as the highest independent honor in India in the field of science and technology for science technology, technology entitled Aviation Cockpit Risk Validation Platform. Other than all these achievements, Dr. Neelam has published more than 25 papers for in international highly reputed journals of international journals of high repute, and published more than 38 conference proceedings and one book chapter. With this, I request Dr. Neelam to over to you, Dr. Neelam.
Thank you, Dr. Shekhar, for such a nice introduction. So I hope I can start with my presentation. I'll share the screen now. Is my presentation visible?
Yes, ma'am, it is.
Okay. So first of all, I would like to thank the organization institutes for giving me this opportunity to discuss some of our work here. So today I will be talking about precision thin film coatings for demanding optical applications. Actually, our institute, which is CSIU, is mainly known for optical devices and systems from the beginning of its inception. And I will discuss more about optical coatings today because apart from that, we also work in some other areas. But before starting with the actual subject, I would like to give a brief, brief feel of our parent organization, that is CSIR. We are basically associated with our CSIR. CSIR is the Council of Scientific and Industrial Research in India, and it was established sometime in 1942. It has 38 state-of-the-art institutes and also some of the centers all over India. And CSIR has expertise and experiences in its, in terms of its scientists and scientific and technical staffs, as well as research students. We also provide human resource development through ACSIR, which is basically Academy of Scientific and Innovative Research, which we will be talking about later. So over the years, what happened is this unique organization served as a main institute in India to do scientific activities in a wide variety of domains like affordable healthcare, aerospace, materials, and chemical sectors. Here I have shown some of the technologies which have been developed by CSIR. And
excuse me, ma'am.
Yes.
Neelam, ma'am, I'm not able to see the full screen.
You're not able to see the full screen?
Please choose,
Okay.
please choose that option.
Okay. Just a minute. Are you able to see it now?
No, ma'am, not yet.
I have made it full screen here.
Chandrasekhar sir, are you able to see?
Not yet. It is just the second
It is full
slide.
screen here.
Can you, Chandrasekhar sir, can you help ma'am?
Madam,
It is already full screen from my side.
okay, but I think it is not visible here. Can we share the screen again? Before exiting and then.
All right, I'll try that then.
Yeah.
So I have put it in full screen mode.
Yeah, now it is visible.
Is it visible now?
Yes.
Yes, ma'am. Yes.
Okay. So I have been talking about CSIR, which is our parent organization. So CSIR has developed many technologies which are well known in India. Like in its initial days, CSIR has developed some Amul spray milk and the indelible ink which we use till date, and we also export this, and some kind of tractors, and also trainer aircraft. So we have the presence all over India, and we at CSIR, we belong here at Chandigarh. So our mandate is basically to develop instrumentation for the sector of societal use, for defense sector, and for any other electronic or agriculture sector equipment also. So we develop different kind of instruments, and for that we do R&D as well as development work. So the mandate of our organization, that is CSIR CSIO, is basically to research, design, and develop scientific and industrial instruments for societal, strategic, and high science applications. So we have our core strength in optoavionics, freeform and diffractive optics in case of optics, and also we work in the area of sensors, actuators, and starting from biomedical instrumentation to computational instrumentation. So it was this center, this institute was established somewhere in 59 initially at Delhi, and then it was moved to Chandigarh. So these are some of the initial pictures which were which are taken during the building inauguration by Dr. Zakir Hussain, and we also have one ISTC center that is Indo-Space Training Center basically. So with this brief introduction about our institute, I would like to discuss few activities which are being taken at CSIO. Actually, we have, as I discussed, we have different components, different research components, as well as our development components and capabilities. And I belong to basically, till now, I have worked in the area of optical thin film coatings, which falls in this case under precision optomechanical and next generation avionics. And also now I have been working I have started working in materials and instrumentation for sensing and related applications as well. So for today's topic, I will be discussing the work which have been carried out under this precision optomechanical and next generation avionics. So as I have already discussed, we work in different area for defense and strategic applications, sensor applications, medical devices, as well as we do high-end science also related to material science, nanoscience and technology. And also nowadays in AI, we also do computational instrumentation. And my major focus for today's talk is basically optics and photonics, in which I will be mainly talking about optical filter and lenses, which we have developed for different optical instruments which are being used in high-end applications. So if we start with optical coatings, then I will say that our core area here is optical thin film coating. And our department used to deal with optical design and fabrication, mechanical assembly, and electronics and software part, where all these components were used for making a particular optical instrument. So we deal with industry, societal, and strategic applications in these studies. So in case of optical thin film coatings, we have our focus areas in which we are continuously working, and we have also gained much strength in these areas. We go for design and fabrication of interference filters, uniform graded index based, and notch and AR and neutral density filters. We will discuss about these filters today, because today we will be discussing only about optical thin film coatings. And along with the fabrication of these filters or coatings for high-end application, we also do the proper testing and characterization of these components, because most of the time these components will be used in some particular instruments which will require qualification and testing as per a military standard also. So these coating has to be done very rugged way, and also they have to be qualified for their use in such kind of instrumentation. So it is a detailed process which involves the fabrication as well as testing and characterization along with calibration of these filters. But today we will be mainly talking about the classification of these filter and little bit of fabrication. So before we start with optical thin films, actually what exactly is a thin film structure? In general, if we see material, we have a bulk structure. Whatever material we take, or crystal structure or any crystalline material or any amorphous material, we have a bulk structure which has some definitive physical properties. Okay, so but sometimes what happens is these bulk structure may not be able to get the required properties what we require for a particular application. So in that case, we make use of thin films. Like if we talk about general semiconductor industry, we have many thin films involved in a particular device fabrication. So why these thin films are needed? Because they will be able to give us some particular characteristics at a low length scale, which can be integrated into very small space. So for these kind of studies, we require thin films. So a thin film is nothing but it is a layer structure where it has dimensions in macroscopic scale, only in length and breadth. Its thickness is negligible small. That is of the order of wavelength of light in this case of optical coatings, because we are talking about only visible spectrum right now, that is starting almost from 380 to 700 or so. So in that area, we will be mainly talking about the thin films where its individual layer thickness falls within the order of wavelength of light in this region. So these thin films are used to manipulate or tailor make the optical properties. Like we will discuss in detail what are the optical properties and how they are tuned to make these optical coatings. So these thin films are basically deposited on bulk materials, which are called substrate in general, and they are required to achieve properties which are attainable or not attainable or not easy to attain on bulk materials. So that is why we coat a particular lens or a particular filter or particular screen with such kind of material, so that we require the we get the required properties. So as I already discussed, these thin films have been commercially exploited with great success in development of devices such as transistors or any electronic component you talk about, or even solar cells and sensors. So with that brief introduction about thin films, now we are coming to the optical coating. So when we talk about optical coating, we require thin films in such a way that they can alter the transmission or absorption of the light inside that coating. So that where we want to use a particular substrate for light transmission in some cases, or light absorption in some other cases, or light reflection. So we can get we are able to get the required transmission and absorption by applying these kind of coatings. For example, if I take an example of solar cell, we have generally the solar cells, we use different kind of coatings for fabrication of solar cell, and we also use some kind of coating on the glass which is covering the solar cell actually. So the purpose of that coating is optical coating actually. So that will be anti-reflection coating which is required so that it does not reflect the sunlight. So but inside the packaging of the solar cell, we use different kind of coatings for its functioning. That is to manipulate the electronic properties of so that it gives us the solar cell response. So when we talk about this optical coating, we have one or more thin layers of material which is deposited on optical component such as lens or mirror, which alter the way in which they reflect and transmit light. So the main purpose of this thin film optical coating on optical substrate is basically to modify or to improve the optical performance. The optical coatings are mainly classified into three main components. That is anti-reflection coatings, which are used for reducing the unwanted reflection. High reflective coating, which are in such a way they will increase the reflection of the light from that surface. And almost 99.99% of the light can be reflected from such a high reflective coating component. And also we have some other type of optical coating where we use the structure in such a way that we want the reflection in certain band of the wavelength, and we require transmission in the outer or the other side of the wave spectrum. So they are called basically the filters, that is band pass filters, low pass filters, or high pass filter, depending upon the requirement of the end product. So when we have to design an optical thin film, we have to take into account the main physical phenomena which takes place when a light falls on a substrate. So the basic concept of optical thin films includes transmission of light, absorption of light, reflection of light, and interference. Whenever a light falls on a substrate, there can be only three cases. Either the light can get transmitted, it can get absorbed, it can get reflected. In major scenario I'm talking about, there could be only three major cases. And also there will be some of the concepts in which the interference of the reflected light will take place from different parts of the substrate, different sides of the substrate. So that will fall under interference. So we have different kind of coating based upon transmission, absorption, reflection, and interference. In today's topic, we will be covering most of the interference-based coatings, which will result in optical filters for some specific applications. But before going to that side, we will go briefly through these basic concepts. So transmittance is nothing but the fraction of the incident light which is which is passing through the substrate at that wavelength. I mean, whatever wavelength it is the source is having. If that full light is passing through the substrate, then we will call it 100% transmittance. But that will never happen actually in some rare cases. If we talk about air or so, and that too, it will not be ideal, never. So, and the other concept is absorbance. In this case, whatever light is falling on the sample, some of it will get absorbed by the molecules of the sample or the substrate. So these molecules will absorb some of the light and they will allow some of the light to pass through. Or maybe they will absorb the light of a particular wavelength or a particular band of the wavelength, and other wavelength of white light will pass through. So this is related to the initial light which is falling, and also this absorbance will give us information about the intrinsic nature of the material through which it is falling, or through which it is passing and being getting absorbed in some extent. And the other concept is reflectance. When we talk about reflectance, the reflected light is basically the light which goes back from the sample surface. If we talk about this surface, say it has some, if we consider it as a single substrate, and then this is the incident light which is coming, and this light will be partially transmitted and it will also be reflected. So what happens is, whenever this light is reflected, so the intensity of this reflected light will be different and the intensity will be different. The intensity of the transmitted light will be different. So depending upon the nature of the substrate, the amount can be calculated. The nature of the substrate means how much is the refractive index, because that is the physical quantity which will determine the optical nature of the material. So depending upon the refractive index of the material, we will see how much reflection of the light is happening. So if we consider the refractive index of the air, which is the medium is the light is coming from this side, and this is the substrate. It has got refractive index of N1, say, and then the reflection at this end will be given by this equation. These are well-known formulas for a light reflection at an interface. So depending upon this physical phenomena, we design many interference filters which will be used for high reflection as well as low reflection in certain region. So after discussing about reflection, now we come to interference. So interference of light happens when there is one or more ray of light which is there, and there occurs some kind of interference between the two. So interference will happen in two ways. Either it will be a constructive interference, where it will result into net increase of the reflection, and other one will be a destructive interference, where it will result into a less reflected light. So based upon these two, there are some physical phenomena behind it, or some equations which we have to take into account while dealing with such kind of interference filters. So depending upon the nature of the material as well as the nature of the medium from where the light is coming, then we can design the filter in such a way that these filter can transmit light in a certain direction, and they can reflect light with a particular intensity at certain wavelengths. So this is a very interesting concept which can be utilized to have these different reflected light filters for different applications. So here again, in general, what happens is interference filter consists of a dielectric layer. This is the dielectric layer. It can be of a single or a multiple half-wave thickness, which is sandwiched between two reflective or semi-reflective coatings. and it will make a dielectric stack, and it will involve multiple internal reflection kind of thing. So what will happen, depending upon the physical parameters of this structure, we can design transmittive as well as reflective filter with very narrow wavelength region also. So why I am showing all this is this background, because what we have done till now, what was a conventional techniques, and where we have reached now as per international standard. So to give that feel, I have gone through these basic concepts, and now this is the schematic of a multi-layer structure where we have optical grade glass substrate. We deposit different kind of layers, and also then we get reflection from each layer, because this whatever light is coming, it will get reflected as well as transmitted, and this light again will get refracted and reflected. So the same phenomena will occur until this light comes out of the glass substrate. So these lights, these rays which are reflected from different interfaces, they will combine depending upon their phase difference and all, and how, whether it is a destructive or a constructive interference. So with that background, we use thin films in optics for various applications like mirrors, high reflected dielectric coatings, anti-reflection coatings, and some hot and cold mirrors, and neutral density filters as well. So as I have already discussed, high reflective coating will involve the reflection to be increased to almost to 100%. That is the ideal condition. We want a mirror which has to be 100% reflective. But that condition may or may not be met many times, because there are a lot number of phenomena which takes place actually at the substrate or inside the module. So this example shows the highly reflected mirror for a laser wavelength of 1064 nanometer. So like this, we can design, and we can have these mirrors which are used in laser tubes. And also we can have metallic mirrors like aluminum, silver, gold mirrors, which are used in various optical instruments, as well as in some consumer applications as well. And also, if for IR application, we use some kind of mirrors made up of gold. And the other aspect of optical coating is anti-reflection coating. Anti-reflection coatings are the ones which are used to reduce the reflection, where we don't want any reflection from the substrate. Because if we consider, say, a single glass substrate whose refractive index is almost 1.52, so if the light comes and it gets reflected from this surface and this surface, even at this one, the reduction of 4.2% will occur. Now suppose we have 4 mirrors made up of this glass, or 4 lenses made up of this substrate. So effectively what will happen, whatever light we are sending, at each lens, the reduction of 4.2% will happen. So ultimately, whatever light we are getting at the other end, that will not be exactly 100%. So the performance of that instrument will really hamper if we use these lenses without coating. So we have to coat these kind of lenses with anti-reflection coating, so that the reflection of these surfaces can be reduced, and we are able to get appropriate amount of light intensity or light transmission which we are seeking in that instrument. So there are various designs available for anti-reflection coating, starting from single layer to multi-layer reflection. They can be designed for a single wavelength where we have the requirement of single wavelength transmission. They can also be designed for a range of wavelength, like for visible optical applications. We can design anti-reflection coating which gives minimum reflection from starting from our 300, 400 something to 700 something. So accordingly, we can design the anti-reflection coating. So these anti-reflection coatings plays a very important role when we talk about where the light intensity is very important, where we have to have the maximum light output when it is coming through these lenses. And also in consumer application, also we use anti-reflection coating in some glasses and even some phone cameras and all. And another type of filters are UV absorbing filters. See, whenever the sunlight is falling in the atmosphere or reaching Earth, so we have a UV component as well. So in some cases, this UV component is found to be harmful for certain applications. So what we want is we have to block this. So we can, this kind of region of wavelength can be blocked by using UV filters. So they can be designed in such a way that they will block the light starting from this range, even below that. The UV range can be blocked and only the visible can be passed for such application, like they are used in front of the lens or STCD or CMOS cameras, which need to be protected from UV. Another component is basically the beam splitters. These are used for splitting a particular beam into 2 or more components. So we have initial light beam, which has to be split either achromatically or dichroic mirrors. Dichroic means 2 colors or single color. It has to. In some cases, the intensity will be same, and in the other case, the color will be the same. So sometimes we have a mirror, which we have a beam splitter, which will split our white light into 2 components. Say only the green and the red component will be transmitted or reflected. So these are called basically beam splitters in optical coatings. And then comes our narrowband pass filters. There are pass filters which are used for passing a band of wavelength. They are called band pass filters. But in some cases, we require, like in laser application, we require a filter which has to be very narrow. Only that single wavelength we want to reflect. So that is the fabrication of such kind of filters is very difficult actually, because reducing this band width is really a very tough process, and it requires lot of iteration, lot of design, and the most important thing is fabrication here is very tedious task, and it involved a lot of tests and trials before going to the final filter fabrication, because we have to optimize the individual layers, because it will involve a stack of thin films which has to be fabricated. Accordingly, we have some nuclear density filters also, which are used to reduce the intensity of the incoming beam. They are generally used in photographic cameras and all, where we use where we have to reduce the light intensity so that we can get proper photographs. So with this, these are some of the typical applications of optical thin films. We have some helmet mounted displays where there are some particular coatings used to reflect the projected symbology. We have some optical filters, and in photography also these can be used. We have beam combiners of some display avionic displays where this green color light only need to be reflected. So we also developed this kind of coating for these beam combiners. And there are some other applications as well, like some in instrumentation, like Raman and confocal microscopy, and consumer application as well. So with this background, we will be talking about mainly of optical interference filters now, which we have developed in our lab. We have also worked on anti-reflection coatings for optical instruments, which were to be used in high-end application. Before we start with the discussion of actually fabricated and designed filter, I will briefly discuss about thin film fabrication techniques. there are various techniques to deposit these optical coatings. However, the technique for this optical coating has to be rugged, it has to be repeatable, and it needs to be upscale, because some of the components require, say, hundreds of layers of coating. So that may not be possible by some other processes. Like in general, thin film deposition involve our sol gel, CVD techniques, MPCVD techniques, and PVD techniques. So physical vapor deposition is one of the best technique which we have used till now for fabrication of these interference filters. We have a state-of-the-art thin film coating facility at our place. We have 4 coating systems, but mainly we use this electron beam coating system for optical thin film fabrication. And in this case, what happens is we evaporate the material by utilizing some electron source, where they will actually evaporate the material which is present here, and this evaporated material will be deposited on the substrate surface. And also the system need to be very precise for optical coating, because here we will be talking about the thin layers in nanometer region. Even if there is a difference of 10 nanometer in each layer, then the final pass band or the peak of the filter will not be at the same place where we have designed for. So we have, this process has to be very precise. So for that we have different kind of thickness controls here. We have quartz crystal thickness control, where it will be determined that how much thickness of this material has been already deposited. So this involves the control as well as the design of the films, which has to be made precisely. So with this we can achieve higher deposition rate also, and too many number of layers can be deposited without any peeling off from the substrate sample. So we have these high-end equipments which we have got recently. We also have thermal coating plant for our metal coatings. So these are the different components which we have developed in our lab using this thermal and E-beam evaporation techniques. We have developed some neutral density filters as well as some reflective folding mirrors and beam splitters. So today basically we will be talking only about the reflective filters because other things, it will take too much of time. So when we talk about optical interference filter, what we require is, we require a reflectance in a particular band, a very high reflectance. That also depends upon the light intensity, how much intensity we want at that wavelength to come out. So depending upon that requirement, we design the filter, and the beauty of this filter should be that it has to be, the outside band, it has to be very less reflection, so that if we want to transmit the highest here, we should be able to see outside properly, because we are developing this for some display applications. So at the same time we need to see outside, and we need also to reflect some of the wavelength. So that depends upon the design and requirement of the end product. So we have designed high pass, low pass, and all band pass filters as well. So if we talk about optical filter technology, we have started with conventional optical filters, which was this technology was developed quite long back, and then we have shifted to graded thickness optical filters, and finally to graded next optical filters. What are the difference between these three, we will be discussing in the coming slides, but briefly I will let you know that conventional optical filters are designed by multi-layer structuring of high and low refractive index materials. The drawback of these conventional optical filters are they have the broad broad wavelength bandwidth. So they are not suitable for the application where we require very narrow bandwidth and high intensity or high reflection. So we have gone through literature, and then we developed some graded in thickness index optical filters. Even there are some of the problem because the side lobes were high. Side lobes means the transmission, the reflection outside the window was also coming, which were not appropriate for some specific applications, because we want only the reflection at a particular wavelength high, and outside we want minimum. And then the third type of filters which we are now developing are graded index optical filters, where we have designed and modulated the refractive index in such a way that we are able to get maximum transmission along with the minimum outside window reflection of the substrate operators. So this is the schematic for the conventional filter, and this is the design of the conventional filter. So we are getting these side lobes as well. So we require only this, and this should be minimum, because here we can see that almost the 15% it is reaching. So we don't want that. So, but still we are able to reflect the green light and also to see through outside. But then we went for modulated thickness design, where we can design the refractive index in such a way that we can find out that the reflection is maximum along with the lower side lobes. This design was also further modified, and we could see that we can have a design in such a way that the conventional design is not gained, and also some anti-reflection layers are used at the end and the beginning, so that the index matching can be done with the atmosphere or with the air in this case. So using that one, we are able to reduce the outside reflection to a quite low value, and also we are able to gain the highest reflection at the desired window. And the next one was actually the index modulated design, where the refractive index in conventional layers jump actually from one value to the other. Say if we use aluminum dioxide and silicon dioxide as a multi-layer structure, we change the refractive index from 1.6 to 1.4 abruptly. That abrupt change in refractive index will result in your side lobes as well as the broadband. So to overcome this kind of problems, we have tried to modulate the refractive index profile in such a way that there is a continuous variation in the refractive index from one layer to the other layer. So using this kind of design, we are able to achieve reflectance, high reflectance inside the band, and low side lobes as well as low reflectance outside. And similarly, this can also be designed for a color display. In a single filter, we can design 3 different colors, like your blue or blue, green, and red can be designed in the single one. Just a minute, please. So depending upon these kind of design structures and all, we have fabricated different kind of filters for avionics applications, and also after optimizing these processes, we developed a beam combiner coating. Depending upon the optimization of this filter, we did some computational optimization for this, and then we did the fabrication using these parameters. So we have modulated the thickness in such a way that the refractive index gets modulated, because the two are related. in when we talk about the multi-layer structure. And also final result, if I show you, this is what we have received. These are the number of layers, almost 44 layer it involves, and this is the substrate, is the VK7 substrate, and also we are able to achieve the almost very low reflection if we talk about outside the window, and highest reflection inside. And this is the actual sample which is shown here. You can see that when the green light, when the white light is on, its green light is reflected. So this kind of application requires basically a single wavelength reflection. So if we talk about the comparison of optical coatings for filter technology, we have seen that initially there were the filter which was just being used like 20% of reflection, but that reflection was happening throughout the spectrum, throughout the wavelength region from 400 to 700. So what was happening, whatever light is, when we want to see outside, I mean, if we have a glass, we want to see outside, but we want to reflect only green color. So that was not happening. Outside color also was going off because there is a reduction almost about more than 30%. And then this red one is the uniform thickness multi-layer. So here the band was quite, the full width at half maximum was quite large. So there also the light intensity was decreasing because it was covering a very broad band. And further, we came for thickness modulated, and finally for index modulated, refractive index modulated design, where we could achieve very low side lobes, as well as, because reduction in side lobe is necessary so that the outside window or outside this window reflection is not increased. So we could achieve this one, and we have got promising result in this case. And this has also been implemented in some of our technologies. So this was all about optical interference filters, which we have developed for our display applications. And along with that, we have done some other work also in case of optical films, which might be interesting to you. If we talk about nighttime glare, see, when we are driving, we have these headlights. When a vehicle is coming from opposite side, suddenly the glare will come, and it will, blind the eyes of the incoming driver. So for that problem, we have developed some kind of coating which could be utilized so that directly on the either on the screen of the car or on the outside the headlights. Both ways. So that coating was done by using neutral density filter, so that we can reduce the incoming glare. So this is the photograph of a light. What is called that generally we use at home. These LED lights, emergency lights. So this is without. This is taken without that filter, and here the filter is mounted in front of that light. So we could see that the glare is reduced quite. So these kind of application will have a huge demand if it can really get commercialized. So we hope that this will be an innovation if it could go to some consumer. So similarly, we using these kind of filter only, we also developed some anti-glare camera module, because that is also to reduce the excessive glare. So these kind of coating can be used anywhere where there is a problem of glares and which needs to be reduced. So this is the general consumer application where these neutral density filters are basically used to reduce the intensity and take the photograph properly. So we can have various range of these neutral density filters which can reduce your transmittance up to 20%, 50% as per the requirement they can be designed. And the anti-reflection coating, as I already talked about, we have developed some state-of-the-art anti-reflection coating which are being used in demanding optical components, and which are which are also MIL standard certified. And recently we have developed some optical coating for protective properties. Now what happens is when we use these optical components in some sophisticated instruments or in some sophisticated structures where these cannot be cleaned again and again. So because they are delicate and they need proper care. So for that purpose, we require some kind of coatings which will not decrease the optical performance of those components, and also they will keep their surface clean. So recently we did some work in that area, and we developed some optical structure where we utilized some particular kind of coating process which is called glancing angle coating process to develop porous structures. These porous structures will result in modification of the surface, and they will not allow the dirt or water to stick or moisture to stick on their surface. So we have done the thorough analysis of those type of coatings, and we have seen that they can be effectively used for this hydrophobic or anti-dust coating kind of thing. So after fabrication of these filters, they, as I discussed, they undergo various property measurements and characterization and MIL standard confirmation. So we use for design, we use different kind of softwares which are internationally renowned softwares for optical thin film design. And also we use UV visible spectroscopy and our spectroscopic ellipsometry for our UV visual optical property measurements, and also for surface roughness and thin film quality measurement, we use interferometry, and also we do mechanical adhesion test and other required standard test, so that our these coatings qualify for their application in different optical component of high sophisticated applications. So these are some of the filters which I have already shown. And we have a huge fabrication and characterization facility at CSIO. We have different microscopic facilities, and also we have some other electrochemical and DLS, and as well as many other characterization facilities which we make use of to develop this kind of coating. So in general, when we talk about optical filters, our main application area is basically avionics, which I have not discussed here in detail because I just wanted to keep it up to optical coating only. So this is the actual symbology, how it appears after coating. So we can see the outward outside scene also, and at the same time we can see the various information of the aircraft as well. So with this, I will say that these optical filters and optical coatings have vast field of applications where they can be used starting from societal to strategic to some instrumental areas, and also in space applications as well. Nowadays, we can utilize optical coating in many ways. So with this, I thank you. And Jai Hind. If you have any questions, or we can have open discussion also.
I request participants to discuss your queries, please.
Okay, there are two questions.
Can I share my unshare my slides now?
Yes, ma'am.
Oh.
Madam Dinesh Babu NR has a question. He says, what are the material used for ND filters? Is it purely coated on substrate of glass by nanomaterial?
Actually, are you talking about ND filters, neutral density filters?
Yeah. ND filters.
Yeah, we use some kind of alloys, actually metal alloys, and it is coated on glass substrate for our initial trials. But it can be done at some other substrate as well. So it is possible.
Participants are requested to post their queries. This is for participants. They may post their queries into chat box.
Okay, any other question for ma'am? Chandrasekhar sir?
Not yet.
Okay. Dear participants, you can put your queries in the chat box, please. Ma'am will reply you as soon as possible. Okay. And thank you very much, ma'am. That was really an adept and extraordinary talk, I'm telling you. And we will look forward to see you again. So thank you very much. And before moving towards the vote of thanks session, let me tell you, my dear participants, a link has already been shared with you in the chat box. Kindly fill the form and get your certificate of participation. The link will be active for next 10 minutes. And so please, I request you to fill it as soon as possible. Chandrasekhar sir, you have already shared the link, I think.
Yes. It is there.
Okay, so it's a time to acknowledge the contribution of all the contributors who worked very hard to make this event a success. So on the behalf of Department of Physics, Amity University, Haryana, and National Sun Yat-sen University, Taiwan, and on my own behalf, I would like to thank our guest speakers, Professor Cheng, Professor S.K. Sharma, and Dr. Neelam, who spared their valuable time with us and shared their firm knowledge with us. I'm very grateful to Professor A.K. Yadav and Professor Preeti Thakur for inspiring us to plan and execute this event. I also would like to thank to Dr. Chandrasekhar, Mr. Rohit, Mr. Amit Kumar, and Ms. Sudha, and IT staff of AUH and other faculty members who helped us in a way or the other. And the most importantly, I would like to thank all the participants to make this event a success. Once again, thank you very much. And participants, please fill up the form given in the chat box and get your certificate of participation. Thank you. Thank you, SK sir. Thank you, Neelam ma'am.
May I close the session?
Just give us only 5 to 10 minutes so that participants can fill up the form.
Okay.
Otherwise, they didn't get their certificate. And I request Professor Sharma and Dr. Neelam, if they want, they can leave the session.
Thank you. Thank
you very much, ma'am. Thank you very much, Yatendra sir. We'll see you again.
Yeah, sure.
If any participant is finding any difficulty in getting the certificate, please let us know in the chat box only.
A participation certificate may be a bit delayed, but make sure you have filled the form and successfully submitted.
If you fill the form and submit it, then you will surely get a certificate through your mail. You will get it on your mail, on your registered mail ID, right, sir? Chandrasekhar sir?
Yes, madam.
The participants who have already received the certificate can leave the meeting. Chandrasekhar sir, can you check how many participants are there? Matlab still in the meeting.
Yeah, 35. And
35.
we have received the response from 35. Yeah,
We have received the, okay.
35 responses are there.
It means 35 certificates have been issued, right?
Yes.
Okay. So we can stay here for 10 minutes more.
Yeah, maybe, yes.
Okay. Chandrasekhar sir, you are on mute.
Yeah, yes, madam.
आज कितने responses हो गए?
Dear participants, just want to inquire, is there anyone who has not yet filled the feedback form? Please write in the chat box if you have not yet completed the form. Because we are going to close the form within 2 minutes or so. If I don't receive any response in the chat box, then I will presume that whosoever is present, they have already filled, and we are good to close.